Hi everyone. Today we are starting section 4.5, derivatives and the shape of a graph. In this section, we are going to use derivatives to understand what a graph looks like, not just specific points, but the overall behavior of a function. So instead of just finding derivatives, now we are going to interpret them. Why this matters? These ideas are important because they help us figure out where the function is increasing or decreasing. Find the local maximum and minimum values. Understand concavity and inflection points. And finally, describe the overall shape of a graph using derivatives. So this is where everything we've learned about derivatives starts to come together. Let's start with the first derivative test. The main idea is simple. The sign of the derivative tells us how the function is behaving. If the derivative is positive, the function is increasing. And if the derivative is negative, the function is decreasing. So think of the derivative as telling you the direction the graph is moving. Here is the more formal version. We assume the function is continuous on an interval. And differentiable except maybe at a few points. Now, let's focus on a critical point, which we'll call C. A critical point is where the derivative is zero or the derivative does not exist. Now, we check what happens to the derivative around that point. If the derivative changes from positive to negative, the function goes from increasing to decreasing. That means we have a local maximum. If the derivative changes from negative to positive, the function goes from decreasing to increasing. That means we have a local minimum. If the sign of the derivative does not change, then there's no local maximum or minimum here. So a local maximum happens when the function goes from increasing to decreasing. A local minimum happens when the function goes from decreasing to increasing. Here are the two key things to remember. Critical points are only candidates for extrema, meaning they might be a maximum or minimum, but not always. A critical point does not always give a minimum or maximum. So we always have to check the sign change of the derivative. We can't just assume. So to summarize, the first derivative tells us if a function is increasing or decreasing. By checking how the derivative changes around a critical point, we can identify local maxima and minima. In the next part, we'll start applying this idea to actual problems. Now, let's talk about how to actually use the first derivative test step by step. I am going to give you a clear process that you can follow every time. Here are the steps. Step 1. Find the derivative f prime of x. Step 2. Set f prime of x equals 0 and solve for x. Step 3. Find where the derivative is undefined. Step 2 and 3 together give us all the critical points. Step 4. Make a sign chart. This is where we figure out where the derivative is positive or negative. Step 5. Determine where the function is increasing or decreasing, and where we have local maximum or minimum. Now, let's apply these steps to an example. We're given f of x equals negative x to the third plus 3 over 2x squared plus 18x. And we want to locate all local extrema using the first derivative test. Step 1. We need to find the derivative. This is the function f of x. Let's differentiate term by term. The derivative of negative x to the third is negative 3x squared. The derivative of 3 over 2x squared is 3x. The derivative of 18x is 18. So we get f prime of x equals negative 3x squared plus 3x plus 18. Step 2, we'll set the derivative equals to 0 and solve for x. So we set the derivative equal to 0, which is negative 3x squared plus 3x plus 18 equals 0. This is a quadratic equation. We can either solve by factoring or by using the quadratic formula. Since this is factorable, so we are going to factor it. First, I am going to factor out negative 3. So I have negative 3 times x squared minus x minus 6 equals 0. Now, I am going to factor x squared minus x minus 6. I have x minus 3 times x plus 2. Next, I set each of these factors equal to 0. To solve for x from here, I add 3 to both sides, so I have x equals 3. And from this equation, I subtract 2 from both sides, so I have x equals negative 2. So, when x equals 3 and negative 2, the derivative equals 0. Step 3. We check if the derivative is undefined anywhere. Since f prime of x is a polynomial, it is defined for all x. So there's no additional critical points from this step. So our critical points are 3 and negative 2. Step 4, we use the critical points to build a sign chart. First, let's draw a number line. Our critical points are 3 and -2. So we are going to place the critical points on the number line. So I have -2 here and 3 here. Our critical points split the number line into 3 different intervals. The first interval is from -infinity to -2. The second interval is from -2 to 3. And the third interval is from 3 to infinity. Now we test each interval. For the first interval, we want to know if the derivative is positive or negative in this interval. So we pick a test point. We can pick any point in this interval. It could be -3, -4, -5, -6, any number that is less than -2. So I'll pick -3. And I take -3, I plug that into the derivative. -3 minus 3 is negative. -3 plus 2 is negative. My derivative equals -3 times this factor times this factor. This factor is negative. This factor is negative. So I have negative times negative times -3. That is negative. Next, we need to pick a number in this second interval from -2 to 3. Let's pick 0. And I take 0, I plug that into here. 0 minus 3 is negative. 0 plus 2 is positive. So I have positive times -3. That is positive. Next, I need to pick a number in this interval. You can pick any number that is larger than 3. So let's pick 5. 5 minus 3 is positive. 5 plus 2 is positive. Positive times -3, that is negative. So my derivative is negative in this interval, positive in this interval, and negative in this interval. So what does it tell us? It tells us that the function, the original function, is decreasing in this interval, increasing in this interval, and decreasing in this interval. Step 5, determine the behavior of the function and find the extrema. Okay, the function is decreasing on the interval from -infinity to -2 and from 3 to infinity. And the function is increasing on the interval from -2 to 3. Next, I need to find the local extrema. At x equals -2, the function goes from decreasing to increasing. So at this point, I have a local minimum. So I have a local minimum at x equals -2. To find the actual local minimum value, I need to take -2 and plug that into the original function to find f of -2. Since f of x equals -x to the third, plus 3 over 2x squared plus 18x. So f of negative 2 equals negative of negative 2 to the third plus 3 over 2 times negative 2 squared plus 18 times negative 2. And I get negative 22. Now, at x equals 3, the function goes from increasing to decreasing. So we have a local maximum at x equals 3. To find the actual local maximum value, we need to plug 3 into this function. So we have f of 3 equals negative 3 to the third power plus 3 over 2 times 3 squared plus 18 times 3. And I get 40.5. So my local minimum is negative 22 at x equals negative 2. My local maximum is 40.5 at x equals 3. If the question only asks for the local minimum and the local maximum values, then the answer is negative 22 and 40.5. However, the question asks for the location of the local minimum and the local maximum. So we need to be able to tell where they are. To do that, we are going to give the coordinates. So the local minimum is at negative 2, comma, negative 22. And the local maximum is at 3, comma, 40.5.